Okay, so in the Computational model, we have some supporting tools to run this model. So the Conca model is based on the Fortran code. So we need some Fortran compiler, likely Intel Fortran compiler, and we will do some data processing. So we choose the MATLAB, or you can if you don't have enough money to buy the MATLAB, you can use the Octave. The Octave is a free software, and also we need to plot some figures and some animations. So also we use the MATLAB or Octave to do this work. So in the first case, I will demonstrate the 2004 Sumatra tsunami. So I will go to many details. The Sumatra tsunami reconstruction about this event, we use 5-segment tsunami initial sources, and this source can be found in the Greelio's paper 2007. So if you want to see more details, you can go to this paper. So from the grid parameters, we can get the initial tsunami wave height like this picture. So in this picture, you can see it's Malaysia, Sumatra, Sri Lanka, India, and Armenia and not this. Sorry about that. So it's the initial tsunami wave height about the initial time. So it's the December 2060. It's about the midnight. So after, we can see the animation start. So tsunami propagate first to the Sumatra directly, and then we went to the Malaysia, and then Sri Lanka and India. So also from this simulation, we can see everywhere tsunami arrival time, and also about the wave height. So in this, in the Conca simulation, we can know the tsunami arrival time, so we can predict the tsunami, also the tsunami wave height. So the second case is about the 2011 Japan tsunami. In this case, we use the papers, the links, 2015 papers parameters. So we use with these papers, magnitude is about 9.1. The focal depth is about 20. And now we are in the stone surge modeling part.
Okay, great. Yeah.
Okay. So I go ahead. If we lose the connection, I will rejoin you again. Okay. Yeah. So the most important situation we want to know from the stone surge is the inundation, because the inundation is directly that cause the damage to housings or buildings, or it can be the potential threats of the coastal communities and be the damages of the roads and bridges. So if the case shows about 2005 Hurricane Katrina. So inundation induced by Hurricane Katrina, you can see is flooded in the cities and the bridges and the roads. All these things are destroyed because of the stone surge and also the waves. And unfortunately, in the Taiwan's regions, we are covered by the severe typhoons track. So Taiwan is here, and now we are very close. Here. So also in the Japan and Philippines and Hong Kong, we are very close to the South China Sea and Pacific Ocean. So in these regions, the typhoon will get enough energy and the heat to become the potential severe typhoons. So from this picture is the typhoon tracks accumulated from the 1951 to 2014. So you could see the Taiwan, Philippines are covered by the severe typhoon tracks. So in these regions, we are not to wonder about the stone surges damages, and also the wind wave and the rainfall and something from typhoons. So also in the stone surge modeling, we use the Conca surge model. The Conca stone surge model is based on the tsunami model, because the tsunami model has some advantages like the inundation calculation and ST grid system. So we use it to develop the stone surge model. So in the stone surge model, we add some physical terms like the pressure gradient terms and wind shear stress terms to make it can calculate the stone surge propagation and also in the coastal regions. So the supporting tools are the same. Yeah, we use the Intel Fusion compilers, MATLAB, and Octave software to do the data processing, and use also the MATLAB or Octave to plot our figures and animations. In the first case of the stone surge modeling, I would like to introduce the case study of 2013 Typhoon Haiyan in the Philippines. Name is about the Typhoon Yolanda. So is the Yolanda track it passed through Regulian and Tacloban and then passed to the China. So we can see that in these regions we will expect the highest stone surge will have observation in these regions. So in order to study this case, the Typhoon Yolanda case, we use the 4-level nested computational domain. And the first layer is the resolution is the 4 kilometer. But we want to see more clear about the stone surge propagation. So we use the second layer. The resolution is about 1 kilometer. So in the 4 kilometers domain and 1 kilometers domain, we can see the stone surge propagation in the deep water region. But in this case, we want to see the coastal stone surge inundation. So we use the more fine resolution domain. The resolution was increased to the 500 meter and almost 100 meter in the Latitude Gulf. In the Latitude Gulf, from the observation, the stone surge height is I think is more than 3 or 6 meter. So I forgot. Yeah. And we also know that in order to calculate stone surge, we need a meteorological input. So in this case, in the Typhoon Yolanda's case, we combine with atmospheric WRF model, and the WRF results are provided by the Professor Lin Chuanyao, also from the Sinica. So in the lab picture, it shows the Typhoon Yolanda's type of wind structure is very stable. But we know that the typhoon structure will be influenced by the topography, and also because it is a vertex, so you have some special phenomenon. So we can use the atmospheric WRF model to capture its check and typhoon intensity. So the two animations shows the pressure fields and the wind fields. So from the WRF simulation, the wind field will reach to more than 50 meter per second. So we use the two meteorological fields input to our stone surge model, so we can get a stone surge propagation in the large computational domain. So the color bar shows the stone surge in the deep water regions. So also, because this circle is in the water is induced by the pressure gradient. When the typhoon center is more close to the Philippines, the wind shear stress effect will become more significant. So from these snapshots of the stone surge in the Philippines, we can see more clearly about the typhoon we are making before making landfall of the Philippines, and when it was passing through the Philippines, and then passing through the Philippines, the different stone surge phenomena inside the Philippines. So we can see the maxima simulated stone type in the Latitude Gulf because we use the most highly fine resolution to study the stone types in the Latitude Gulf. So the maxima stone type is more than 1 meter. We can simulate it to do in this part, and also in the Tabanu. In these regions, the stone surge is more than 1.2 meter per second. So in these regions from some scientific reports or some field surveys, they are under the threat of the stone surge induced by the Typhoon Yolanda. Okay, the second case about the demonstration is about the operational stone surge prediction in our Taiwan region. So here it shows the case about 2016 Category 5 Typhoon Nippon in Taiwan. The Typhoon Nippon is a severe typhoon, and the typhoon intensity will reach to the Simpson, I remember it's 5, a Category 5 hurricane. So it's the typhoon structure is very stable from the satellite image. And the typhoon's track is located in the Pacific Ocean originally, and then the path is direction is to Taiwan directly, and then we make landing for at the Taiwan and go to the China. So in our stone search operational test, we will do stone search maybe per a cycle for 3 hours. And if we use the WOF or TWOF model, we can do a prediction per 6 hours. So if you start the model and then use the input, we can run the stone search and then output the results per hour. So a cycle for 3 hours or a cycle for 6 hours. And if the typhoon is leaving, so we will exist this circle. And the inputs for the stone search modeling is about the type of meteorological forcing and tidal boundaries. And the results will get the 48 hours time series for stone tide and the pure tide at the specified tide locations and two-dimensional products to see what the stone search propagation and then the dangers. So it's just some simple pictures to show the stone search run and pure tide run. We will do the 2 days forecasting and the 2 days warm up about the stone tide simulation, and then we can do the pure tide run about the 4 days. And in the operational task, we use the 2-level nested grid domain for the operational. The first layer is about the 8 kilometer. The second layer is about the resolution is 2 kilometer in our Taiwan. But because the resolution is not enough, because of that, we want to do the operational missions. So the resolution cannot be too fine. And the grid information of this domain is we use the layer 1 and a second layer. So the green numbers is layer. And the bathymetry database we see from some public resources. So the first layer, we use the Etopo1's database. And the second layer, we use the GAPCO database. So the resolution, the resolution is about 8 kilometer and 2 kilometer. And also we want to know the tide validation, the tide is correct or not. So we need to do the tide validation before we do the operational system. So in our Taiwan, we could see in some specified tidal locations is the Tochen, Dawu, and Anpi is located in here, here, and here. The tide prediction is close to the harmonic data. So from these results, you can see our tide prediction is very accurate. So we have enough confidence to do the stone search prediction. So it's the case by the typhoon Nipok. It's the stone search propagation in the 2 days prediction. It's also the maximum stone surge in the 0 hour to the 12 hours in the future, also 12 to 24 hours. So we could see in this duration, in this period, the stone surge will be the most dangerous to the Taiwan regions. And also in this case, the stone surge can be calculated for 2-day prediction and only spend 1 hour on the PC labels computational resources. So our Conca has a very high speed efficiency. And from the resolution, residual means that the stone tide minus the tide in these durations. So we could see the residual more than 1 meter in the east part of Taiwan, and also the 0.8 meter stone the residual in our west part of Taiwan. So from the pictures observation from some reporters, we can see the surge and wave in our Taiwan is very large. Yeah, so it validates our prediction. And the third case is about the severe typhoon Merenti. The Merenti is also the most severe typhoon in last year. The central pressure has reached the 900 millibar. So the typhoon intensity was very strong. And so in this case, we just show some 3-dimensional demonstration of the stone surge modeling in a deep water regions. So the blue bodies are the water in the deeper regions. The green are the lands. Yeah. So you could see this is the stone surge. So if we see the sea level scale about the stone surge, you could see the almost the 1.10 meters the stone surge go to Taiwan directly and then passing the stars part of the Taiwan and then went to China. And also in in this case we will demonstration about the high resolution stone surge inundation calculation in Taiwan. So the case is about the Typhoon Sudiller in 2015. About this case, in the Typhoon Sudiller, the track is very similar to the previous cases, and also it caused some much heavier rainfall in the inland in our north part of Taiwan. And in this case, it has some special situations. We use nested computational domain in the open ocean and offshore regions. The resolution is about it's about 2 kilometer. I remember. And in the second layer nested grid, the resolution is about 1.0 kilometer. And in the coastal regions, we divided the coastal Taiwan regions to different computational domains. The high resolution is about 200 meters. So also we want to see this case from the large scale simulation. So we use the largest computational domain on spherical coordinate system to do this simulation. It's about the pressure field and the wind field. And in this case, we can see the stone surge in the Pacific Ocean and then passing to Taiwan and Taiwan's chains and then to the China. And also in this case, we do the coastal inundation calculation. The left picture shows the stone tide, the inundation induced by the stone tide. The stone tide's meaning is about the stone surge plus tide. So it's the coastal regions in our Taiwan. And the right-hand side is about the pure tide, is a pinto. So if you compare the two pictures, you could see the stone surge inundation, the inundation induced by the stone surge. And our results can be combined with the GIS Google Earth software. So it's the coastline from the Google Earth. And the blue colors and red colors are our results from the inundation. So we could see the inundations length and the areas from after we combining with the Google Earth software. And our results can also compare with the observation data from our Central Weather Bureau's observation data in specified tide locations in the Suao, Donggang, Nanwan, and Kaohsiung. The red lines are the simulation done by the T-Wolf simulation, and the red lines are done by the parametric typhoon model. So the results are good after we compare it with the observation. So it proved our models. It also, the time is enough. So the conclusion, and here we demonstrate the tsunami modeling about the 2004 Sumatra tsunami and the 2011 Japan tsunami. We demonstrate the two cases about the tsunami modeling. And in the stone surge modeling, we have 4 cases. The first one is the Typhoon Yolanda in the Philippines, and the other 3 are some Taiwan's local cases about the Sudiller report and the Moranti. These 3 cases are induced by the severe typhoons. And after we demonstration about the stone surge and the tsunami modeling, we have the eye-contact cloud surface established and developed by the Sinica computational centers. And also the ice surge, it means that the stone surge prediction service, I think it will come in soon, maybe. Okay, so I finished the demonstration of the stone surge and the tsunami modeling, and welcome for discussion. And if you have some comments or questions,